What is life cycle analysis? Make sure that we know the meanings of upstream emissions, embodied energy, and embodied carbon dioxide, and know what co-products are or displaced products, and we're going to use biofuels as our example. So life cycle analysis is when you consider everything. What's the full effect? And there are several different life cycle analysis we can do. We can do a financial life cycle analysis where we talk about costs. We can do an energy analysis. We can do an emissions analysis, pollutants analysis, etc. And we can think of the full effect either to the consumer, to society, or to the company. So embodied energy, it's all the energy that goes into producing a product. So we have everything from straw bale at 1/4 megajoule per kilogram to aluminum at 227 megajoules per kilogram. So it's worth noting you would need about 5 kilograms of the equivalent of 5 kilograms of petroleum to produce 1 kilogram of aluminum. However, recycled aluminum has a much lower embodied energy because the largest portion of energy for aluminum refinement is extracting the pure aluminum from the ore. However, if you're trying to find out what is the life cycle energy input of a product you're making, if you make it out of aluminum, you can't say, oh, I'm going to make it out of recycled aluminum because that will have lower embodied energy. It's kind of like marginal electricity. We have to think about when you start to buy more aluminum, well, people are already recycling as much aluminum as they can. So when you take more aluminum, that extra aluminum for your production is going to come from mining. And so your product is going to bear the full 227 megajoules per kilogram of embodied energy. It's interesting to look at steel, has a much lower ratio. So for aluminum, the ratio of embodied energy for taking new material to recycled material is 28 times for aluminum and only 3.6 times for steel. So let's take a look. You've heard the cocktail party conversation. I could buy a more fuel efficient car, but then there's all this energy that has to go to making my car. Let's look at the embodied energy in our vehicles. It turns out that for devices that are made to use energy, the energy they use during their lifetime is going to be much greater than the embodied energy of making the device. So this would be for your light bulbs, for any heater, for motors, for cars. It turns out that the embodied energy in a car is about 1/10 the total energy it's going to consume in gasoline. So this is a report that making a typical automobile from virgin materials used about as much energy as each year's driving. That presumes, of course, that people drive on the order of 15,000 miles a year. We can test this, just a back-of-the-envelope calculation. We know that steel is 36 megajoules per kilogram, and let's say it's about a ton of steel in the car. And let's compare that with, we drive 15,000 miles at 30 miles per gallon. That's 500 gallons. Multiply that by the embodied energy in gasoline, and we come up with 62,500 megajoules. But certainly, the processing of the car is going to require more energy. So when we consider more processes, this number is going to get bigger, and to me these numbers are close enough to the same. Now the question is, where do we draw the boundaries? There are all kinds of processes that go into making a car, including, for instance, the workers in the steel plant driving to and from work, or their children getting to school on a school bus. And where we draw the boundaries usually are, what are the processes necessary to make the product? What the people do in their outside lives, they're going to do regardless of what product they make. So when we think about the embodied energy in a product, we think about only those processes that go to make that product. And it could include transportation to the factory if that is somehow particular or special, like the fact that people have to fly to the factory. We remember Alex Farrell's publication is a life cycle analysis of the carbon emissions from different fuels. We recognize the greatest portion of the carbon emissions comes from engine exhaust. That's 20 grams of carbon per megajoule of petroleum. But there's also these processing costs in getting the gasoline to you that vary depending on the technology. And so then you say, well, what about biofuels? In biofuels, that engine exhaust comes from plant carbon, which comes from CO2 that it takes out of the air. So we don't count this when we talk about burning biofuels It's just the processing carbon dioxide that we add to the atmosphere. And it sounds like a great idea until you realize how huge this can be. For instance, British Petroleum, the biofuels division, said, "Isn't this great? The carbon dioxide comes right out of the air into the biomass. We do this processing, and ultimately we burn it and put the carbon dioxide back in the atmosphere. Perfectly cyclic, resulting in no increases in carbon dioxide." But then you look at, okay, we need fertilizer, we need fuels for the harvesting, energy in the processing, refining and distillation, all of which produce carbon dioxide. During the fermentation process, carbon dioxide is produced, as people who make bread or beer know. And how about land use? Well, we're using more land, we have to put water on it, a considerable amount of water, and there's also runoff. With that fertilizer runoff, it produces biological oxygen demand. What this is the fertilizer produces algae blooms, in particular in the Gulf of Mexico, and when all of this matter dies, it decomposes and kills a large section of the Gulf of Mexico. This is called eutrophication. When we consider all of the processes associated with bioethanol, biofuel, what they find is that the processes involved in making the bioethanol, especially land use changes, result in more carbon dioxide being emitted than if people had just used gasoline. And there's also other consequences. The increased demand for food raises the cost of food. And we also find out that considerable subsidies, so this is an external cost for all of us, are required to make this industry profitable. Okay, then you say, let's take a look at diesel. At present, the life cycle analysis would be you get it from an oil reservoir and you burn it and it emits CO2 and pollutants. Also, there are upstream pollutants. And then you think, okay, biodiesel would be a great idea because then the CO2 that we emit goes back into the soybeans. But again, you have all of these processing and upstream emissions that constitute a considerable amount of carbon dioxide. In particular, land use changes, because this ultimately is going to come from deforestation. There was a study done on Indonesian biofuels where they grew palms, and with the palm oil they made biodiesel. And it turns out that in order to make these plantations in Indonesia, they had to burn the rainforest. But more importantly than the forest itself was the many meters of peat that was stored up underneath the forest floor. And what the study concluded was that there was so much carbon emitted in the burning of the peat and the rainforest that these plantations would need to renewably produce biofuels for 500 years to pay off the carbon dioxide debt that resulted from establishing these plantations. And so we can take a look at, for instance, life cycle greenhouse gas emissions for different technologies. Here we have soy biodiesel, which is actually greater than diesel produced from conventional oil. The greatest carbon dioxide emission is in land use change, in that you need land to grow this stuff on, as opposed to driving an electric car with electricity derived from natural gas. Land use change can be very indirect. For instance, because of corn ethanol, less farmers grow soy. So where are we going to grow soy? We're going to grow it in Brazil. In Brazil, they're going to clear more land by burning rainforest. What about biodiesel from the waste stream, from food? This seems to be a great idea because we have to grow the soybeans anyway, and after we fry the food with the soy oil, we just throw it into a landfill. So if we now use it for biodiesel, we don't have to take responsibility for any of these upstream emissions for growing the soybeans. So now we have to look at where would this oil have gone? And it turns out that it doesn't go to landfill. It goes to animal feed. So why does that change our analysis? Because we can't do without animal feed. And so now you have an agricultural industry that needs to support this new animal feed, and all of these upstream emissions associated with the agriculture are attributed to your use of biodiesel that you diverted from the animal feed stream. So we can see that the consequences of our decisions are not always as obvious as we would think. Okay, so what about co-products? Certainly something good must come from this. And how would we account for that? So for instance, when you make biodiesel from agricultural soybean, the biodiesel isn't the only thing that comes out of it. You get a co-product of the solids. These solids have nutritional value and are usually used for animal feed but can be used for human beings. So how do we account for this? Well, what energy would have gone in to producing the animal feed to begin with, and what emissions would result if we had to grow this animal feed from agriculture that we no longer have to do now because it's a byproduct or a co-product of our soybeans. We do this by subtracting off these agricultural emissions from the original emissions of our soybeans. Let's take a look at a life cycle analysis study. Now, this is an energy life cycle analysis, not an emissions and not a financial. We're looking at the energy on the y-axis for 4 different processes. And this is megajoules of energy in the biofuel. So here we're looking at corn grain ethanol and soybean biodiesel. And we're producing 1 megajoule. Here is the production. Megajoule output in the biofuels. And these are all the different inputs from agriculture and processing. We can see for corn grain ethanol, a significant amount of processing is done to purify the ethanol. And we can see that there's only a little bit of extra energy produced, and actually some studies show that you have to put more energy into the corn grain ethanol than you actually get out from burning it. Over on this side, we account for the co-products. So now you can see if you produce 1 megajoule of biodiesel, you also produce about 0.7 megajoules of feed for cattle or people, and a smaller amount for corn solids in distilled dry grain solid. This is not the caloric energy you get from burning or eating this co-product. It's the amount of energy you would have had to put in the agricultural sector to produce it. This is an interesting graph that shows the amount of carbon dioxide equivalent for a whole bunch of consumer products. This is carbon dioxide per dollar that you spend, and this is carbon dioxide in upstream emissions per gram of product that you buy. You can see that beef has a much higher carbon footprint than vegetables, this yellow circle down here. But as a self-righteous vegetarian, I have to be honest and say, look, what about cheese, which is just as bad as beef, versus chicken? Chicken is approximately like a vegetable as far as the carbon dioxide equivalent. We can compare gasoline at $2 a gallon, and now it's about $4 a gallon or even more. This would be the carbon dioxide that you emit as a result of purchasing your gasoline. And this line is the 44 divided by 12 in grams of carbon dioxide emitted divided by grams of fuel purchased. So you might have heard that trading in your Hummer for a Prius is the equivalent to becoming a vegetarian if you used to eat a lot of beef. Livestock emit as much carbon dioxide as the transportation sector. And so let's take a look at some food that we eat. What if we eat beef and we eat tofu? We need 2 pounds of tofu to provide us with approximately the same amount of dietary calories, although the different nutritional aspects will vary. Those are the costs to us as a consumer. What about the upstream costs? For instance, this tofu required much less land, much less water, and 1/700th the amount of carbon dioxide emissions as livestock. So we can look at what is our global footprint. We have on the average of 1.9 hectares per person. A hectare is 100 meters times 100 meters. And what do we need this land for? These have been calculated. This graphic explains what we need land for. We need land to supply us with the minerals that we mine and the energy that we need. We need it to house us. We need it to process our waste, that would be carbon dioxide waste or garbage. We need it to supply us with food, and we need it to supply us with fiber. So this is a very interesting graph where it shows that the amount of land we use has been increasing over a period of time. And the units it uses are number of earths that we're using. Note that while the number of earths that we use has been increasing in time, our total number of earths that we have has remained constant at 1. I went on sabbatical to Berkeley to study biofuels because I thought that this was going to be the answer to our energy needs. And in doing these life cycle analysis, I became aware that the consequences, the environmental consequences of biofuels were arguably much worse than just using conventional fuels. And I did so through understanding upstream emissions, embodied energy, embodied carbon dioxide, and how you use co-products or displaced products.